In this third video, we're going to move away from the physical properties and we're going to look at some of the chemical reactions of these period 3 elements. And remember, these trends in the chemical properties are referred to as periodicity. We'll consider the reactions of these elements with oxygen, and we'll also consider reactions with chlorine. And then we're also going to look at the variation in the oxidation numbers of these oxides and chlorides, and then how to explain this variation in terms of outer shell or valence electrons. Now, this won't be a very long video. A lot of it will be where I direct you to videos that you can watch to make certain observations. And when we get the opportunity, when we back in class, we will look at some of these demonstrations so that you can make some of your own observations. The period 3 elements react with oxygen to form the corresponding oxides, and you're going to have to watch those videos to look at the flame colors and to make some other observations as well. But generally, the equation will be the element plus oxygen gas O2 will form the corresponding oxide. It's for some of these, you can work out the correct formula of the oxide quite easily just by using the charges or the valencies. But for others, you're going to have to learn and memorize the most common oxide formed. I'll quickly just talk through these, and then you can refer to these observations when you watch the videos. So sodium oxide will react quite vigorously if you burn it in a gas jar containing oxygen, and the flame color there will be a yellow flame when the sodium reacts with oxygen to form the oxide sodium oxide. So how can you work out the formula for sodium oxide? We know sodium is in group 1, so it will have an ion of the charge of 1 plus. Oxide, group 16 or group 6, so 2 minus. So we need 2 sodium ions for every 1 oxide so that the charges cancel out, therefore Na2O. Magnesium is one that you've seen before when we covered the group 2 elements. And we know that magnesium burns with a bright white flame and also reacts vigorously with oxygen to form the oxide magnesium oxide, which is a white solid. Sodium oxide, in fact, is also a white solid. If we look at the formula, magnesium oxide, to write that formula, we know we have Mg in group 2, so 2 plus, oxide is 2 minus, therefore the formula MgO. And you can apply the same thing for aluminium plus oxygen forming aluminium oxide, where aluminium ions will have a charge of 3 plus. The aluminium oxide will also react vigorously with oxygen if it is in the powdered form, because generally aluminium is covered on the surface with a thin layer of aluminium oxide because it does react with oxygen quite easily, but that initial layer on the surface will actually serve as a layer of protection to protect the aluminium on the inside. But in the powdered form, aluminium will also react vigorously with oxygen and will also burn with a bright white flame. Phosphorus reacts vigorously with oxygen. If you expose white phosphorus to oxygen, as soon as you take it out of water, it would start to combust spontaneously, and the flame there will be a bright white flame. It can also be described as a yellow flame, and you will see kind of white clouds of the phosphorus 5 oxide produced. So that's quite important, that formula, or that systematic name, phosphorus 5 oxide. So the most common oxidation state of phosphorus in the oxide will be 5. So the formula for that one will be P4O10 that you're going to have to remember going forward. Sulfur, if we burn sulfur in a gas jar containing oxygen, it will burn quite gently. It will burn with a blue flame, and it will form mostly the oxide sulfur dioxide, also known as sulfur 4 oxide if you use the systematic name. But we know that sulfur dioxide can be further oxidized to sulfur trioxide or sulfur 6 oxide. For these equations, please don't go and memorize each individual equation. Make sure you know the general equation, the period 3 elements plus oxygen gas. So O2 gas will form the corresponding oxide. Yes, for phosphorus oxide, the P4O10, you're going to have to remember that specific oxide formed, and that we generally mostly form SO2 or sulfur dioxide gas when sulfur reacts with oxygen. But generally, it will be good enough if you remember the general formula and you can apply it to any of the specific elements. So practice writing out the equations for the rest of these reactions. So I've given you the one here where aluminium reacts with oxygen gas to form aluminium oxide. So in terms of state symbols, if you wanted to add those in, so aluminium is a solid, oxygen is a gas, and aluminium oxide is a solid. So you can also add those in. So the other elements in period 3, chlorine and argon, they will not react with oxygen gas, so no equation that you have to remember for those two elements. If we then move on to the period 3 elements with and their reaction with chlorine to form the corresponding chlorides, again it's useful to know the general equation. So it will be the period 3 element plus chlorine gas, Cl2, will form the corresponding chloride. Only one product formed, the chloride formed. But for some of them, you're going to have to learn the specific formula of the chloride. For most of them, though, you can work it out using charges and or valencies. If we look at one example, sodium metal reacts quite vigorously with chlorine gas. If we burn a piece of sodium in a gas jar filled with chlorine gas, it will be quite a vigorous reaction to form sodium chloride, which we know is a white solid. Okay, that's general table salt. Magnesium will also react vigorously with chlorine to form magnesium chloride, MgCl2. Aluminium will do the same. Also a vigorous reaction with chlorine gas. But this is quite an important formula to remember. It is not AlCl3 as you would expect. Yes, it first of all does form AlCl3, but it will then combine with another one of these aluminium trichloride units to form what we refer to as a dimer containing two of these units. So it will be Al2Cl6. It should look familiar. We looked at the structure in aluminium in Al2Cl6 in quite a lot of detail when we did structure and bonding, and it's important that you practice to draw that dot and cross diagram showing the dative covalent bonds and the normal covalent bonds. Moving on to silicone. Silicone will react only very slowly with chlorine gas to form the chloride, silicone tetrachloride. Again, you don't have to memorize that one. You know silicone is in group 4, so valency of 4. Chlorine group 17, valency of 1, therefore SiCl4. Phosphorus is in group 5, so it forms the chloride PCl5, okay, which is also a very slow reaction. One reaction which is not added on the slide here I see at the top is the reaction between silicone and chloride to also form the corresponding oxide, silicon dioxide, SiO2, and that is also a very slow reaction between the silicone and the oxygen. So you can probably, let's just add that in here. Okay, so in addition to all of those elements, we also have silicon dioxide or silicon 4 oxide formed when silicone reacts with oxygen. Obviously that one will fit in there in that series of compounds if we keep it in order of the periodic table. As with the oxides, have a go, practice writing out all of these equations for the other reactions. So you're given sodium, do the same for magnesium, aluminium, silicone, and phosphorus. The reaction between sulfur and chlorine, you don't have to cover these reactions for the exam. There are certain chlorides formed between sulfur and chlorine, like SCl2, S2Cl2, but it's not going to be something that we cover. And then the last thing we need to look at here will be the reactions of some of these elements with water, and the only ones we'll consider will be sodium and magnesium. Magnesium we've done already, so I'm not going to go into any detail again. We've looked at the reaction between magnesium and cold water. That one, it's extremely slow. Magnesium in steam, which is a more vigorous reaction, which will then form the magnesium oxide instead of the magnesium hydroxide. But let's just quickly talk about the reaction between sodium and water. It's something that you hopefully would have seen in previous years as a demonstration, and I did post a video on that on the website as well. So sodium reacts quite vigorously with water. It floats on the surface. There's a lot of bubbling or fizzing that you will observe. The reaction is very exothermic, so it gives out enough heat to actually melt the sodium metal, because it's got a relatively low melting point. So we actually observe a molten ball of sodium floating, running around on the surface of the water, and eventually the sodium will disappear completely if it reacts fully with the water. And in the process, that fizzing is the H2 gas, or hydrogen gas, being produced, which we can test with a lit splint and then a pop sound. And it will also produce the alkali sodium hydroxide, which will be a compound which dissolves quite readily in water, so it will be in solution. Before we look at some practice questions, let's just consider the trends and oxidation numbers of these period 3 oxides and chlorides. So have a go at doing the following. Work out the oxidation numbers of all the elements in the following compound. So do it for all the oxides and all the chlorides. Let's just add in silicon dioxide or silicon 4 oxide in here as well. So SiO2, and work out the oxidation state for the silicon. We know oxygen is -2, so 2 times -2 is -4, so silicon must be +4, so that overall the oxidation numbers add up to 0 in that compound. And we apply those rules to work out all of these other oxidation numbers or oxidation states as well. So oxygen we know is always -2, except in a peroxide, and none of these are peroxides. So all of these oxygens will have an oxidation state or oxidation number of -2, and you can use that to work out the other elements. But all group 1 elements will always be +1, all group 2 will always be +2, aluminium will always be +3, and we can use oxygen being -2 to work out phosphorus here as +5, was 10 times -2 is -20, so we must get to +20, so we need 4 times +5, and that's why the oxidation number or oxidation state of phosphorus here is +5. And here we have sulfur dioxide and sulfur trioxide. Oxidation state of sulfur here is +4 and +6. So we can use that to name these compounds using the systematic naming system, where we show the oxidation state. So this is referred to as sulfur 4 oxide. Okay, so sulfur, and then in Roman numerals a 4 oxide, and sulfur 6 oxide. That's how we distinguish between the two oxides. So the sulfur dioxide and sulfur trioxide is kind of the older naming system. And we can also work out the oxidation states of the elements in their chloride compounds. And please note, as shown here by the sulfur compounds and phosphorus in this case with the chlorides, these elements won't always form compounds with the highest possible oxidation state. Okay, sometimes we can form some other compounds where the oxidation state is different. Before you attempt these questions, I really suggest that you watch as many of those video clips as possible to get a better idea of the reaction or the reactions of these period 3 elements with oxygen and then also with chlorine. It's going to be really useful for when they ask you to name certain visual observations. Chlorine reacts directly with many elements to form chlorides. 3 such compounds are magnesium chloride, MgCl2, AlCl3, and SiCl4. State and explain the pattern shown by the formulae of these 3 chlorides. If we look at the number of chlorines in each one of these formulae, we can see we go from Cl2, AlCl3, and SiCl4. So every time the number of chlorines increases by 1. okay, or it matches the group number as well. We know magnesium is in group 2, aluminium group 3, and silicon group 4 or group 14. But generally, state the trend there. That would be the number of Cl increases by 1 each time. And we have to explain it as well. Why is that possible? Why is magnesium only MgCl2 but aluminium AlCl3? So you have to consider the electron configuration, the number of valence electrons as stated in that learning outcome right on that first slide. So as we go from magnesium to aluminium to silicon, there's an increasing number of valence electrons or outer shell electrons. Okay, so therefore, there's an increasing oxidation number for each of these elements as well. In the next 2 lessons, we will consider the reactions of these chlorides with water and also the reactions of the period 3 oxides with water. So these questions I'm going to leave now. We will do some of these examples later once we've covered the 4th and the 5th lessons. The elements in period 3 of the periodic table show different behaviors in their reactions with oxygen. Describe what you would see, so some visual observations when separate samples of magnesium and sulfur are reacted with oxygen. So the one with the magnesium you should have seen before in that video lesson on the group 2 elements. And I hope that you've watched some of these other video clips on the website as well, so that you can have a better idea of the observations that you will make when magnesium reacts with oxygen and sulfur reacts with oxygen. And you need to write an equation for each of the reactions as well. So for magnesium, that's probably the easier one of the 2 at this stage. We know that magnesium burns with a bright white flame and eventually forms a white solid or a white smoke of magnesium oxide. And the equation for that will be the element plus oxygen forming the period 3 oxide, or MgO in this case. And then moving on to sulfur, it's a new one for this lesson. As mentioned earlier, sulfur burns with a blue flame, okay, and you can also state that the yellow solid disappears as it reacts with oxygen, and the equation there will be sulfur plus oxygen forming sulfur dioxide, okay, not the one undergoing further oxidation to sulfur trioxide. Okay, it first forms sulfur dioxide, SO2. If they ask for state symbols, it would have been Mg with a little s in brackets, which is a solid, O2 gas, and MgO is also a solid. It's a white solid, so brackets with a little s. And this is not the only way to balance it. You could have a kind of multiple of this as well. So if you had 2 and a 1 and a 2, that would also be a correct way of balancing it. And here for sulfur reacting with oxygen, sulfur also starts out as a solid, a yellow solid reacting with oxygen gas, so a G to form SO2, sulfur dioxide, which is a toxic gas, but the state symbol will be a G. The table gives some data for elements in the 3rd period and some of their compounds. So in the first row, we've got the type of bonding in each one of the elements, then the formula of the oxide, and then the formula of the chloride. Complete the table to show the bonding in the elements and the formulae of the oxides and chlorides. So let's start with the first one, the type of bonding. Magnesium is a metal, so the type of bonding will also be metallic. Aluminium, the same, also metallic bonding. Silicon, we know, forms a giant molecular structure or giant covalent structure, but anyway, the bonding there is covalent. Please make sure you can distinguish between bonding and structure. Okay, so the bonding is a type of bond, is a metallic bond, ionic bond, covalent bond. The structure is whether it forms a giant structure or simple molecule, and is that giant structure a giant ionic lattice or a giant metallic lattice or a giant molecular or covalent lattice. The next row, the formula of the oxide. So sodium oxide, so we know that that one is Na2O. And you said you can use charges or valencies to work it out. So sodium oxide, Na2O. Magnesium oxide, MgO. Aluminium oxide, Al2O3, because aluminium is 3 plus oxide 2 minus. Silicon forms silicon dioxide, SiO2, and then they've given us the phosphorus 5 oxide and sulfur dioxide. Moving on to the formula of each one of the chlorides. So aluminium will form AlCl3, but we know that will combine, two dimers will combine to form Al2Cl6. Silicon with its valency of 4 would form SiCl4, silicon tetrachloride. Phosphorus with a valency of 5 will form PCl5. Sodium reacts with water. Describe as fully as you can what you would see when a piece of sodium is reacted with water. So in this question, again, it would be useful to answer this after you've watched those video clips. But anyway, hopefully you remember some of the descriptions from earlier on in this video. So a few descriptions would be: sodium floats on the surface. There's a vigorous or violent reaction. You're going to observe fizzing or effervescence as a gas is produced. The sodium melts to form a little molten ball or a sphere of sodium, and eventually the solid will disappear after reacting completely. The reaction of sodium with water will be the metal plus water forms a metal hydroxide plus hydrogen gas, or H2 gas. So that would be sodium. I'm going to add state symbols in for this one as well. So solid plus water, a liquid, forming the metal hydroxide, sodium hydroxide. And this is a very soluble hydroxide. All group 1 hydroxides are very soluble. So it will be in solution. So I'll add in the state symbol AQ plus H2 gas, or hydrogen gas. And to balance this equation, you need to put a half in front of H2. You could also have 2 Na, 2 H2O, 2 NaOH, and then 1 H2 gas. Just getting back to the highly soluble sodium hydroxide formed. So because it's so soluble in water, we're going to have quite a high concentration of hydroxide ions in solution. So what will that do to the pH of the solution if there's a high concentration of OH minus ions? So that's the opposite of an acidic solution. Remember, if we had lots of H plus ions we get from an acid, the pH will be very low because it will be very acidic. So if we have a high concentration of OH minus because of the very soluble sodium hydroxide, we're going to have a very high pH. Okay? So something along the lines of 12 to 14. And then the last one of the practice questions for this video: the elements of the third period of the periodic table form chlorides of general formula EClX, where E represents the element. These chlorides show a variation in oxidation number from sodium to sulfur. Use the information given to complete the table below. So you're given the formula of different chlorides, and we have to use that to calculate the oxidation number of the element in the chloride. So let's just look at the question first. By considering the electron configurations of the elements, explain the variation in oxidation number in the chlorides from sodium to aluminium and from silicon to sulfur. Well, let's get back to part 1. Use the information given to complete the table. So let's work out the oxidation number of the element in each one of these chlorides. We know sodium is in group 1, so it's always +1. Magnesium group 2, so always +2. Aluminium is always +3. You could use the fact that the chlorine is -1 in each of these compounds, therefore sodium must be +1, magnesium +2, and aluminium +3. But we're not always sure of the oxidation number of chlorine, and we know that sodium is always +1, magnesium always +2, and aluminium always +3. The silicon will be +4. Phosphorus, if it's PCl3, 3 times -1, so -3, so phosphorus must be +3, and sulfur, 2 times -1, -2, so sulfur in this case will be +2. by considering the electron configurations of the elements, now explain the variation in oxidation number of these chlorides. First of all, from sodium to aluminium. So as we go from sodium to aluminium, the oxidation number increases from +1 to +2 to +3. So why is that? We have to consider electron configuration. So let's quickly consider how many valence electrons we find in each one of these elements. Sodium has got 1 valence electron, or 1 outer shell electron, magnesium 2, and aluminium 3. So how do they react with chlorine? So all of these are examples of ionic compounds, ionic bonds formed. So sodium forms an ion with a charge of +1. So it loses 1 of its electrons. It loses its valence electron. Magnesium loses 2 electrons, so it loses 2 valence electrons, and aluminium loses 3 valence electrons. Why do they do that? Okay, to become more stable, because after losing 1, 2, and 3 electrons respectively, they end up with a full outer shell, okay, or with a configuration that's the same as a noble gas neon. And then if we consider silicon, phosphorus, and sulfur, they have 4, 5, and 6 valence electrons respectively. So for them to get a full outer shell, or an octet of electrons, they need to gain or share their outer electrons. Okay, so silicon will share or gain 4, phosphorus needs 3 more, and sulfur 2 more to give them their noble gas configuration.